We're Team JAAC, and this is ReTread Power. Every year, 280 million tires are discarded in the U.S. alone, but current recycling methods pose serious environmental and efficiency drawbacks.
About 32% of end-of-life tires ends up being burned, which then releases toxic chemicals. Another 32% is turned into crumb rubber, which goes into asphalt, playgrounds, and turf fields.
An additional 17% is sent to landfills each year. These materials leach into stormwater.
Without proper standards and regulations, these materials pose serious safety concerns and have hugely negative environmental impacts.
Modern tires are built to last, packed with rubber polymers, oils, carbon black, and additives. One key component is 6-PPD, which prevents the tire from cracking. When 6-PPD reacts with ozone, however, it transforms into a new compound, 6-PPD quinone or 6-PPDQ. This toxic byproduct washes off roads and flows into stormwater systems, affecting natural ecosystems and wildlife.
But even more concerning, playgrounds and artificial turf are often made of crumb rubber. The EPA has found that these fields contain a cocktail of toxic chemicals, from benzene to volatile organic compounds, and yes, 6-PPD and its derivatives. Under sunlight and heat, they release toxic chemicals into the air, exposing children and others who come into contact with them regularly. The U.S. Tire Manufacturers Association claims their products pose no significant threat, but we spoke to some of the people who did this study, and they disagree. They're also scared about the effects.
So who's right? That's still up for debate. Conflicting studies, project cancellations, and data gaps makes it harder to draw firm conclusions. That's where our project comes in. We're determining just how toxic recycled tires are, and more importantly, we're determining a method to clean them, removing these carcinogens and making it safer for people and the planet.
But we're not stopping there. After the crumb rubber is cleaned, we're also proposing a new way to upcycle the tires, one that transforms the waste into a resource, specifically as a carbon-rich anode for lithium or sodium-ion batteries. We'll come back to this later.
First, to assess the toxicology risk, we use trusted bioindicated zebrafish. These small fish are transparent during early development, which makes them a powerful tool in toxicology. Why? Because their genetic makeup closely mirrors ours, and their fast development allows us to real-time see the effects of chemical exposure on their development, behaviors, and organs.
Exposing embryonic zebrafish to tire particles has caused a range of deformations and even death in some cases. Common phenotypes that we've observed include heart malformations, developmental delays, swim bladder malformations, and necrotic liver tissue. These findings highlight the potential toxic effects of tire particles on aquatic organisms at the early stages of their life, and also clues to the potential harm they could cause to humans.
We also looked into the effect of 6-PPD itself on the zebrafish. We were able to find that concentrations of 50 parts per million of 6-PPD and above caused 100% mortality of the fish within the first 48 hours. We were also able to find that concentrations even as low as 3.2 parts per billion of 6-PPD, which is comparable to the concentration of stormwater runoff from cities, cause underdevelopment and lack of pigmentation in these embryonic zebrafish.
Using solvent extraction techniques, we were able to extract 6-PPD from pulverized crumb rubber. This allows us to study not just the presence of the chemical, but its potency, pathways, and how it might be removed. Cleaning the dangerous compounds from recycled tire material before they hit playgrounds and parks. Using our treatment method, we've been able to extract more 6-PPD than when the crumb rubber is left in water. Our most successful treatment method was using cyclohexanone solvent, where we were able to extract over 5% of the 6-PPD in the tire. This may not seem like much, but when the treated and untreated samples were put in solution and exposed to zebrafish, the treated sample resulted in no mortality of the fish. Recycling shouldn't come at the cost of public health or ecosystems.
With data centers, EVs, and AI driving up electricity demand, we're all looking for ways to advance energy storage. Some major challenges in the field include cost and scalability, supply chain constraints, safety, and environmental impact.
Given everything we've told you so far, we're thinking the same thing. If there are so many tires sitting around and we can treat them for toxicity, why aren't we using them to advance energy storage?
So what if we tell you that we could provide a more stable supply chain for materials,
lower the cost of batteries, and reduce the environmental impact of tires.
The good news is, we can.
The next part of our project looks to treat and convert tire tread material into a hard carbon material, which will provide a low-cost, accessible, and effective alternative to graphite for lithium-ion batteries and a promising anode for sodium-ion batteries. Come with me.
Over the past 4 years, lithium-ion battery manufacturing has almost tripled, reaching 2.5 terawatt hours since 2023. Despite this expansion, the United States and Europe only account for 13% of global manufacturing capacity. However, the landscape is expected to shift significantly. By 2030, manufacturing capacity is projected to expand nearly fourfold relative to current levels.
Lithium-ion batteries are the go-to choice when it comes to energy storage. And they're great, but the problem is that there's not an infinite amount of supply of lithium in the world, and its extraction is not very sustainable. For this reason, sodium-ion batteries are emerging as promising alternatives for lithium, and they're really creating the pathway for diversification, particularly for applications in urban mobility and stationary energy storage, where cost and safety are critical conditions.
Welcome to the lab. A key constraint to the scalability of sodium-ion batteries lies in the supply chain for the hard carbon anode. While the cathode and electrolyte systems can be adapted from the existing lithium-ion platforms, the anode material, specifically the production and processing of the hard carbon, remains underdeveloped. This creates a bottleneck that limits near-term commercial deployment.
Hard carbon is commercially available today, and it's been getting a lot of attention. The most common way to make hard carbon is to use biomass or carbon precursors and heat them at high temperatures, usually using a furnace like this. Biomass, such as wood or cellulose, is good for the environment because it comes from plants and trees. On the other hand, tires are bad for the environment, and they're difficult to dispose of. So we figured out a way to use the carbon precursors in the tires and make hard carbon.
From rubber to the anode. How do we go from an elastomer, an amorphous polymer, to a conductive material that shows crystallinity and structure? First, we etch the material by putting it in an acid bath, which will create defects in the structure. Then, we move to the tube furnace, an oxygen-free environment, where our tire materials, which is a disordered atomic structure, slowly become more ordered, producing conductive hard carbon. Remember when we created those defects? Those defects are now pores that will allow for ion transport into and out of the structure. We mix our hard carbon with a binder and more carbon to cast a slurry. After drying the slurry, we bring it into the glove box. When assembling lithium-ion cells, it is important to add a sufficient amount of electrolyte, which will allow the lithium ions to travel from the lithium disk at the positive terminal to our hard carbon material on the negative terminal. Once assembly is complete and the cells have been properly sealed, we take it out of the glove box and test its electrochemical properties using a potentiostat. Let's now see how this compares to hard carbon.
You may be wondering, what was the point of all of that? Well, I'm here to tell you that we were able to optimize both the acid treatment and the heat treatment to make hard carbon out of our tire material. The best acid treatment was a sulfuric bath at 120 degrees Celsius overnight. The best heat treatment ended up being a set of 2 steps. First, you heat up the material at 400 degrees Celsius in air for an hour, and then you heat it up to 1200 degrees in nitrogen for 3 hours. This gave us hard carbon that we were able to cycle with both lithium and sodium. And the lithium cell ended up showing that we got a specific capacity of 310 milliamps hour per gram, which ends up being comparable to the commercial hard carbon that's currently being used in industry. So not only were we able to take some tires out of our streets, recycle some of that waste, but we're also able to make batteries that cycle with comparable values to commercial hard carbon, effectively killing 2 birds with 1 stone.
Our project addresses environmental and energy challenges by integrating toxicity mitigation with circular material reuse to enable safer recycling practices and a more sustainable energy future. Using zebrafish as a bioindicator, we've shown that the measurable and severe toxicological impacts of 6-ppd in tire materials. We've proved that it's possible to detoxify used tires by removing the carcinogenic 6-ppd compound, and beyond that, we've transformed tire waste into something valuable, synthesizing hard carbon itself, and producing batteries with comparable specific capacity to commercial hard carbon. From energy storage to environmental cleanup, our approach tackles 2 urgent problems: waste and energy, all at once.